Hello everyone, welcome to Meritnation YouTube live session. This is our third and last session of modern physics. Hello Priya, hello Rajesh. So students, in this session basically we are going to discuss few questions based on hydrogen spectrum. Okay, so let's see. So you can see first question on your screen. Hello Ganesh. So students, here you can see as an electron makes a transition from an excited state to ground state of hydrogen like atom ion. Okay. So these are the options and we need to check which of the option is correct here. So basically we need to think about the kinetic energy, potential energy and total energy of an electron. Okay. So let's see here. First of all, let me give you just idea about the total energy, kinetic energy or potential energy. So students, let's see here. First of all, we already know that the relation between the kinetic energy, potential energy and the total energy. This is kinetic energy Ke. Here kinetic energy is equals to K Z E square upon 2R. Okay. And what about the total energy? Total energy is equal to minus K Z E square by 2R. Okay. And what about the potential energy? In potential energy minus K Z E square by R. This one is the potential energy. Okay. So students, now next we can do one thing here. We can relate kinetic energy, potential energy and total energy. Hello, Sanitya. So let's see here. So students, you can see here we can say that the magnitude of kinetic energy is equal to the magnitude of total energy. See this one, total energy here. Okay. And if we talk about the potential energy, so potential energy is equal to what? See, potential energy is equal to here I can say that twice of total energy. Potential energy is equals to what? Twice of total energy. How? Let me show you. See here, this is KZE square by 2R. Okay, this one R is equal to 2 into KZE square by 2R. Okay, so see, this is equal to, so we can see here, potential energy is equal to twice of total energy. So students, we can use these relations in above numerical. Let's see, one more thing here I can show you. Students, for hydrogen and hydrogen like atom, total energy is given by this relation. E is equal to minus 13.6 upon n square. Okay, this electron volt. Okay, you can see this is what this is for hydrogen and hydrogen like atom. Okay, so from this relation you can see here E is directly proportional to minus of 1 by n square. Okay, minus of 1 by n square. And the students, total magnitude of total energy is equal to magnitude of kinetic energy. No? So I can say that kinetic energy is directly proportional to plus 1 by n square. Okay, and what about the potential energy? So students, for potential energy, I can say here potential energy is directly proportional to minus 1 by n square. Okay, so we can use these three relations for above numerical. So let's see here. Here you can see as an electron makes a transition from an excited state to ground state. Okay, so electron jumping from excited state to ground state, it means n of the electron is decreasing here. Okay, so basically here n is decreasing. So student, if n is decreasing, okay, here n, if you talk about the kinetic energy, if n is decreasing here, so kinetic energy is increasing. Okay, see here I can say that kinetic energy is increasing here. Okay, because n is decreasing. But if we'll talk about the total energy and potential energy, you can see here negative sign. So this here negative sign, but in case of kinetic energy we are getting here positive sign. So n is decreasing, kinetic energy is increasing. But in case of total energy and potential energy, this is just opposite. Okay, this is just opposite. So which of the option is correct here? So see here, its kinetic energy increases but potential energy and total energy decreases. So here correct answer is option D. Okay, not option because student, here kinetic energy is positive but total energy and potential energy is what? Negative here. Okay, so if n is decreasing, so total energy and potential energy will decrease here. Okay, so this is all about the first question. Okay, 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 princess. So now we can use different color. Okay, fine. We can use yellow. So now let's talk about the next question. So you can see on your screen next question. In the hydrogen-like atom, electron makes transition from an energy level with quantum number n to another with quantum number n minus 1. Okay. If the frequency of radiation emitted is proportional to what? So we need to check here. Okay, basically frequency is either proportional to n square or something else. We need to check here. So students, we already know that E is equal to what? H c by lambda. Okay, so lambda is inversely proportional to what? Total energy, I can say. Okay, and what about the frequency? So E is equals to nu. Okay, so energy is directly proportional to nu. So student, here electron is jumping from, I can see, energy level with quantum number n, with another with quantum number n minus 1. So here jumping from n to n minus 1. Okay, n minus 1. So students, now we know that E is equal to what? Okay, E is equal to minus 13.6 n square. Okay, so suppose this is E1. Okay, this is E1 minus 13.6 n square. What about E2? So here E2 is equal to minus 13.6 n minus 1 whole square. Okay, n minus 1 whole square. Okay, so students, now we can find out here delta E. So delta E is equal to what? Minus 13.6 n square minus of minus 13.6 n minus 1 whole square. Let me erase this. Okay, here we can discuss this one. So delta E is equal to, we can take here minus 13.6 n square. Okay, minus plus 13.6 n minus 1 whole square. Okay, so I'm taking here 13.6 common. So we are getting here 1 upon n minus 1 whole square minus 1 upon n square. Okay, so we can further simplify this. So let's see what we are getting here. So 13.6 n square minus n square plus this one is minus 1 plus 2n upon n square into n minus 1 whole square. Okay, this is what we are getting here after doing calculation. Okay, just a second. So now next, what we can do here, let's see here. Okay, what happened? Simran, is it visible now? Simran, is it visible? Okay, so here this one is cancelled. So 13.62 n minus 1 divided by what? N square n minus 1 whole square. So student, basically we need to check here. We need to check here the frequency of radiation emitted is proportional to n or something else. So student, energy is what? This delta E is equal to H into nu. Okay, this delta E is equals to H into nu. What we can see here, students, let's see here. Here we are getting n square, and from this bracket we can see we'll get n square. Okay, so this is what? N raised to power 4. In numerator, we can see this n. So in numerator we are getting n. So student, mu is directly proportional to n divided by n raised to power 4. So I can say that mu is this n cube. So this is inversely proportional to n cube here. Okay, so the correct answer is option D here. Okay. Okay, so here correct option is D, because you can see here this one is 2n minus 1. So from this 2n minus 1 we can say here n. Okay, and here this is n square and this is n minus 1 whole square. So the maximum power of n here will be n square. So n square into n square, n raised to power 4, and this n. So after solving we are getting here 1 by n cube. Okay, so this is all about this question. Now move on to the next question. So you can see, or you can see on your screen, the wavelength of first spectral line in the Balmer series of hydrogen atom is 6561 angstrom. Okay. Now next one, the wavelength of the second spectral line in Balmer series of singly ionized helium. Okay. So in above case, we were talking about here hydrogen atom, and after that we are talking about here helium. Okay. Now next thing, what we can do here, let's see here. So students, we know that E is equal to, suppose this is for Lyman series. This is for Lyman series. Here n is equal to 1. Okay, in Balmer this is n is equal to 2. Okay, and this is Lyman. This is for Paschen, n is equal to 3. And suppose this is n raised n is equal to 4, and so on. So student, if we'll talk about the Balmer series, first spectral line of Balmer series, so this will be the first spectral line. Okay, from 3 to 2, this is first spectral line. First spectral line. Okay, first spectral line for Balmer series. So student, here we are talking about the first spectral line for Balmer series. So for Balmer series, and we are talking about the hydrogen atom. So this one is for hydrogen atom. Okay, now what about the next one? Okay, and if we'll talk about the next one, so here next one is for helium. Okay, and second spectral line. So student, this will be the second spectral line from 4 to 2. This is our second spectral line. Okay, second spectral line. Okay, second spectral line, and student, this one is for helium. Okay, this one is for helium. Okay, now we can use this formula. You can see 1 by lambda is equal to r z square 1 by n1 square minus 1 by n2 square. We can directly use this formula here to get the answer. Okay, so let's see here. So this is 1 by lambda rz square 1 by n1 square minus 1 by n2 square. Okay, so student, let's talk about the first spectral line, and first spectral line is for hydrogen atom. Okay, that's great. So this one is here, first spectral line, and that is for hydrogen atom. Okay, so for hydrogen we can take here the value of z is equal to 1. Okay, and here wavelength is also given here 6561 angstrom. Okay, that's great. So here lambda 1 is given 6561. So we can directly use this. Suppose here this is 1 by 6561 angstrom is equal to r. Here z is 1. Okay, and first spectral line means what? Here here from 3 to 1. This is what? 3 to 1. That is the first spectral line for here Balmer series. Okay, so we can take here 1 by 2 square minus 1 by 3 square. Okay, suppose this is equation 1. Okay, this is for hydrogen atom. Okay, first spectral line of Balmer series. Now let's talk about the second spectral line. So second spectral line, and that is for helium. Okay, this one is for helium, and we need to take here the value of z is equal to 2 for I can say helium. Okay, so now here we need to find out lambda here. Na? So suppose this is 1 by lambda is equal to r, and here z is 2. No? So 2 square. Okay, and second spectral line means what? Here 3 to 1. Okay, this will not 3 to 1. Here 4 to 1. See, this is 4. Here this one, let me show you. This one is 4 and this one is 2. Okay, and for first spectral line 3 to 2. Okay, so here I can take 1 by 2 square minus 1 by 4 square. So these are the two equations. So students, we can easily solve these two equations. We can divide equation first by equation 2, and after solving we'll get here the value of lambda. Okay, after solving equation first and second, we can easily get here the value of lambda, and we'll get option A, 1215 angstrom. So this will be the answer here. Okay, this will be the answer. Okay, this is all about this question. Now move on to the next question. So let's see here. Let's talk about the next question. Just a second. Okay, so this one. So student, here you can see the largest wavelength in the ultra. Okay, just a second, something is wrong here. Okay, here the largest wavelength in the ultraviolet region of hydrogen spectrum is 122 nanometer. Okay, that's great. The smallest wavelength in the infrared region of the hydrogen spectrum is what? We need to find out for the smallest wavelength here. Okay, so students, we are talking about largest wavelength for ultraviolet. Na? So students, see here. Suppose this is n is equals to 1, ground state, first excited state. Okay, and this one is what? Second excited state. This one n is equal to 3, so on. Okay, and suppose this one is it. Here n is equal to infinity. Okay, so student, we also know that we also know that E is equal to what? hc by lambda. There is an inverse relation between the energy and the wavelength. Okay, there is an inverse relation. It means more the energy, less will be the wavelength. Okay, so if we are talking about the largest wavelength, no, largest wavelength, that is only possible when difference of energy is very, very small. Okay, when difference of energy is very, very small, in that case wavelength will be large. Okay, so here we can take this one, we can use this formula: 1 by lambda is equal to rz square 1 by n1 square minus 1 by n2 square. Okay, so student, energy difference, first of all, if we'll talk about the if we'll talk about maximum lambda, maximum for maximum wavelength, okay, energy should be what? Energy difference should be minimum. Okay, and that is only possible in 1 to 2. Okay, if we'll talk about the ground state and the first excited state, so between that energy difference will be minimum. Okay, so it means wavelength will be maximum here, so we can use this. So we can use this relation. So 1 by lambda, okay, and that is already given here, 122 nanometer is equal to r, and we are talking about the hydrogen like atom, so here z is what? 1 here. Okay, not hydrogen like atom here, I think we are talking about the hydrogen. Let's see, just a second. We're talking about hydrogen. Okay, hydrogen spectrum. Okay, so fine, let's see here what we can do. So student, so this is 1 by 1 square minus 1 by 2 square, and this is our equation first. Okay, this is our equation first. This is for largest wavelength. Okay, largest wavelength. Now let's talk about the minimum wavelength. So that is only possible when the difference of energy is very, very large. Okay, so we can take and difference of energy is large between first and what? This one. Between this, energy is what? Maximum. If energy is maximum, it means wavelength is very, very small. Okay, so for this one, what we can do here, let's see. So here we can take 1 by 1 by lambda minimum, okay, is equal to r 1 square. Okay, 1 square 1 by 1, and this is 1 by infinity square. Okay, so students, we can easily solve these two equations. And we can get the value of lambda. Just simply divide equation first by second, and do the calculation. You'll get approximately 823 nanometer. Okay, okay, approximately we'll get here 823 nanometer, and this will be our answer. Okay, so now move on to the last question of today's session. You can cross check, Swapnil. Okay, so let's see here, last question. So here you can see the electric potential between a proton and an electron is given by this relation. Okay, so here potential electric potential is given here. Okay, that's fine. So students, now next thing, so we need to assume here, suppose assuming Morse model to be applicable, write down variation of what? Rn with n. Okay, and being the principal quantum number. So student, basically here electric potential between proton and an electron is given here. Okay, so here electric potential is given. First of all, student, we can easily find out the potential difference, potential energy, I can say, because potential difference is already given here. So potential energy is what? Potential difference into charge. Okay, so V into Q. Okay, V into Q here. So student, here I can say that potential energy is Q V naught ln R by R naught. This is potential energy. Now this is potential energy. Now what we can do here, simply student, we can use the relation between the force and potential energy to get the value of F. How? Let me show you. We know that force is equal to what? Force is equal to minus of du by dx. Okay, this is a relation. Force is equal to minus of du by dx, but we know that we need to only think about the magnitude here, so we can take here mod. Okay, so mod. Okay, so let us differentiate this with respect to r, because here r is variable, so du by dr. Okay, and student, what is the differentiation of ln r by r naught? So you can say 1 by r naught into 1 by r naught. So I think we are getting here only 1 by r. Okay, we are only getting here 1 by r. This is the differentiation of ln r by r naught. So here F is equal to what? Q V naught into 1 by r. So this is what? This is the force. So we got here the value of force. Okay, we got here the value of F. And student, you can see here electrons are revolving around the nucleus. No? Electrons are revolving around the nucleus. So I can say that this force is providing the required amount of what? Required amount of centripetal force here. Okay, required amount of centripetal force. Okay, that's fine. So student, F is equal to what? F is equal to mv square by r, and this F is what? Q v naught upon r is equal to mv square by r. Okay, mv square by r. From this relation we can get the value of v, and I think we are getting here q v naught by m. This is what? This is v. Okay, and next student, we need to think about here variation of r with n. Variation of r with n. So students, we know that mvr is equal to what? Mvr, just a second, mvr is equal to what? Mvr, just a second. Okay, something is wrong here. Okay, so here what we can do here, mvr is equal to nh by 2 pi. We can use this relation. Let's see. Okay, mvr is equals to nh by 2 pi. Na? This relation. Okay, angular momentum is equal to what? Integral multiple of h by 2 pi. So from this, what is r? I can say that nh upon 2 pi into m into v. This is r. So student, we can put the value of v here. We can put the value of v. You know, this is the value of v. You can see v is equal to what? Here, v is equal to, see, this v is equals to q v naught by m. Put here that value v. Okay, and after doing calculation, you can see we are only, we will get only r directly proportional to n. Okay, after doing calculation, we'll only get this r is directly proportional to n. So here the correct answer is what? Here the correct answer is option A. Okay, so this is what, this is here correct answer. So students, let's talk about the let me show you one more thing here. So student, in this example, you can see the largest wavelength in the ultraviolet region of hydrogen spectrum is this. Okay, so we took here 1 and 2. Okay, 1 and 2. So students, now next one, the smallest wavelength in the infrared region of the hydrogen spectrum to the nearest integer. Okay, so one thing, student, here if nearest integer is not mentioned, okay, so we can assume, we can take this one. See, from infinity to what? Infinity to first, if nearest integer is not mentioned here. But in this question, nearest integer is mentioned here. So near, because we already took here first and two for what? First and two for minimum, for largest wavelength. So for minimum wavelength, we can do here, we can take here infinity and 3. Infinity and 3. Okay, so infinity and 3. So for second equation, we need to take here infinity and 3 instead of taking here 1. So be careful with this. Okay, 3 is square. Okay, so student, so this is all about today's session. This is all about today's session. So okay, so student, this was the last session of modern physics. Okay, third and last. So see you in next session. So thank you so much, everyone. Next session will be on semiconductor. Okay, so thank you so much, everyone. Take care. Bye bye. Thank you so much. Thank you, everyone.